Hello class, today I'm going to show you how you can simulate airflow and temperature counter in your office or inside any cavity you have. And let's start with drawing. Before drawing, I need to tell you something about the complex geometries. If you feel it's a bit difficult to draw in space claim, so go for ANSYS, SolidWorks. So I'm going to do the same. I'm going to open SolidWorks because I'm much better in SolidWorks. I can draw whatever I want and then save it as IGS file or any other types and import in my Fluent ANSYS. Open part. For this one, I'm going to simulate my office. So let's go for the top plan. Draw a rectangle. And edit it. Okay, 1 meter, 2 meter, 3 meter. My office is about 4 meter length. And 1, 2, 3, almost 3 meter there. So it is a rectangle 4 meter by 3 meter. Let's consider wall 10 centimeter. And this wall 10 centimeter. Okay, now let's extrude it 1, 2, and 3 meters. The height of those walls. Let's close the button. I'm going to close it by a rectangle and extrude it again 10 centimeter. Let me check that. Let's go inward because we already had 3 meters height. Okay, now this is my office. Here it should be my door, which is cooling system situated here. So let's place a cooling system there. A rectangle, select. Yeah, it's pretty close to the ceiling, so around 60 centimeter. So 60, no more, even more. 90. I'm just giving these dimensions visually, so I'm not sure. And the height is much smaller. It's about 50. Okay, this is going to be my Aircon. And at the bottom of my entrance door, there is another, like a window. It is working as a vent. So I'm going to have inlet here and outlet there. So let's simulate that one too. This almost the same size, so I'm just copying it. Let's copy at this direction, and I need copy this, and this. Go down, go 2 meters, and then a little bit higher. Yeah, it should be good. let's extrude it. Yeah, 5 centimeter, and go inward. So it is clear for us what happened. Oh, I didn't. Okay, let's edit this. Delete. So if I want to go inward, I need to select cut extrude. Five centimeter, done. So this is going to be my inlet and outlet. Also, I have a large desk here. So let's draw that desk too. It comes up to, yeah, even here, then here, here, yeah, it's good for this part. And here I need to have a chamfer. So this is the one. Why it doesn't show? Okay. Oh, I needed to change it. Go 50. Still so small. Even bigger. This is 200. Done. Okay, this is my desk. Let's extrude that one. It is going to be about 1 meter. Yes, 1 meter is good. Done. This is my desk. But the under desk is empty. I want to go make it as much as possible close to my office. So let's shell it. And so here it is going to be my drawer, so it's going to be closed. So I'm going to shell it 2 centimeter. Okay. Let me have a cross view. Okay, I'm going to change this to 10 centimeter. I don't want to shell the rest of building. Okay, now it's better. This is my desk. Let's check everything. Empty here, empty, yeah. So it is, air can trap about this side too. Also at the bottom, it's open about 20 centimeter. Let's create that open here. Yeah, and cut that one. So there is open. Yeah. Okay, this is my office. But you know, for Fluent, I don't need to simulate the solid parts. I need to simulate and draw the fluid parts. So to do that, I'm going to use a trick. So let's draw here another rectangle. And I'm going to tell this rectangle to extrude, not blind, up to surface up to next. Yes. Okay. And I don't want you to merge it. So it is going to create another geometry inside this, which is going to extrude up to the next surface we have. Surface we have. Let's do that. And it's not merged. Now let's go insert, features, and find combine. Okay. Now we have three options: add, subtract, common. I'm going to subtract those two. For the first one, let's select this one. Second one, the cut one. Show preview. I'm checking it if I'm right or not. Yeah, as you can see, now I have geometry for the fluid, and SolidWorks cut all the solids out of it. As you can see, my desk area is empty, but inside desk, outside desk is just geometry, which is part of fluid. So this is correct. I want this one. Okay, happy. Now let's save it as a IGS file. Let's go number AP12, create a folder, call it my office, and save it as a IGS file. Oh, what happened? IGES, my office, and save it. Done. Now let's start with our workbench and open Fluent. Where are you? Fluent is here. Let's import geometry. Browse, my office, IGS, and it's ready. I'm going to open mesh. Okay, this is our geometry. Because you remember, we always need to put some names for the important parts. This is my import, so inlet I mean. So I'm going to call it inlet, and this is our vent, so I'm going to call it outlet. With these names, ANSYS automatically is going to recognize and put the proper boundary layers for that. Yeah, for the rest it's okay. Let me check. Yeah, inlet and outlet. Let's check the mesh generation. Oh, it's very coarse. So I'm going to, for sizing and the relevance center is coarse, let's go for fine and see how much improvement we are going to get. Yeah, much better. And how many mesh we have? 39,000. Yeah, good. Let's close this, update, make sure all the data is transferred, and we have a green check there. Okay, let's open setup. I want to have double precision and parallel processing. Use at least 4 CPU cores. And now we have Fluent page. Okay, for this workshop, I would like to have a steady state simulation. That is why steady state is selected. We want to have a gravity, and it should be at negative y direction, so negative 9.81. Let's open model. I want to have temperature, so I'm turning on energy equation, and laminar flow is good. Let's open material. Air and aluminum is selected. I'm happy because I want to just simulate air. I'm happy with that one. Let's check the cell zone conditions. Make sure the cell zone condition is set for fluid here, and that fluid is supposed to be air. If you wanted different properties or different fluids, you need to check here. Sometimes Fluent is going to select the first one as a default, so you need to check these things. Next step is going to be our boundary conditions. For inlet, because I named it inlet, at ANSYS automatically, Fluent automatically recognized it is going to be inlet, so assigned velocity inlet. But you need to specify what type of velocity we have there. So I'm going to 50 meters per second and gauge pressure 0. And temperature 273, so it's cold. For outlet, because it's an outlet again, it's outlet pressure. When we say outlet pressure, it means it's a gauge pressure 0 for outside. We're not considering any pressure here, and ANSYS is going to calculate everything inside and extrapolate pressure for this part. So it's kind of easiest way of assigning pressure for outlet, and if it's connected to the outside pressure, we usually go for outlet pressure. For the wall, again, these are the walls we have for the chair and the side walls. ANSYS is going to consider them as a stationary one and no sleep condition, which we are happy with it. No problem with that. If you want to assign any temperature for the wall, you can assign here, or heat flux or heat generation, but I don't want to consider any heat generation for the walls, because it could be conditions. You say, oh, my wall has a heating pipe inside which is going to generate some heat, so you can specify that heat here. Okay, we are happy with the boundary conditions. Now the rest is okay. Let's go initialize it. Hybrid initialization, no problem with initialization, and let's go for run. 500 would be enough, and start calculations. Okay, simulation finished. Let's close this, or just minimize it and go for results. Okay, let's start with Streamline. I would like to start from inlet and put 250, and the variable is going to be velocity, 250 points. Variable is going to, let's see. So this is flow pattern or velocity pattern inside my office. As you can see, it is mainly going to hit to the top side on the right of the wall, and then the cold air is going to come behind my back when I'm sitting behind my desk, which is going to be okay. And then we have less fresh air or cold air at the front of the desk, and the main, let me decrease the number to, for example, 100. Now we can see more. Yeah, so mainly it is with high velocity, comes here, circulates a little bit behind my desk and goes under this gap to the other side of desk. And we have flow getting out. As you can see, the velocity increases because it's like a venturi phenomena happening here, smaller cross-sectional area. So when flow goes through that cross-section, the velocity increases. Okay, let's see flow pattern as a cross-section. I can change this. Let me turn off this streamline and create a contour for temperature and see it. I should select this is for inlet, this is for outlet. As you can see, higher temperature here, but the rest is cooler. But to have a better, I need to define a surface here to have a better result. So let's create a plan. It should be Z and here at the center. Now let's go back to this, and I'm going to select this plan. So contour for that plan, and I want temperature to show. Not big deal there. Let's see velocity. Now we can see higher velocity here. It comes here. We have even high velocity there, but lower velocity area, almost zero velocity there. If you want to check other sections, let's increase to 50 and apply. So it is going to be much more smoother. I can change the position of that plan. For example, to here. Now you can see how it is moving. Or let me turn off these. I can create isosurface. For example, for here. And for color, let's go for variable, and that variable is going to be velocity. Let's see. So this is a velocity pattern at that surface. Now let me put it this way, decrease the size. Now let's create a video for that, for my ISO face. Now you can see velocity pattern all over the room. Okay, now I can change this to pressure. Let's check for pressure. What about Streamline? Because we already prepared Streamline. Okay, too much calculation, I don't want it. Okay, so you can do a lot of things with this type of simulation. It's enough. See you next time.